any of you who has experience of working in the wet lab or who is working there right now, can we explain what is cyclic? What I can't pronounce it.
Oh,
Cyclic.
cyclic voltammetry, that's what I do
Oh,
in
yeah.
Seth's lab.
And tell us
So
about it.
or
I don't.
Oh my
know.
God.
No, also up to the front.
Oh, I have to go, I don't know if I
Up
can
to the
explain it very
front.
well.
you go up front if you want.
We did our best.
Is it enough?
Well, we
need
have
a
our
laser?
windows. We see both sides for what I'm doing anyway, not just the one where you want like the nice duck curve, but so you have your,
Quack,
the
duck
duck
curve.
curve, it's duck shaped. So you have
Yeah.
your reduction and then your back oxidation, and I'm not really sure what it can tell you because we haven't had very good luck with our machine recently. It hasn't been working very well.
Oh,
And so I haven't been able to get much research done, but I don't really know how to explain it because Wyatt doesn't really understand it either.
That's okay. I have no idea about it at all. So you have my what's concluded.
I don't think
I
any
don't know
of us
anything
have
about that.
like experience with that except for the lovely Elsa.
I thought you were like
Lovely two
the
times.
expert in it.
Yeah, come on, Elsa.
I'm looking, give me a freaking
Time,
second.
every group meeting, you'll be, drawing the shades and everything.
Yeah.
Give myself plus 2 points Ava in group meeting.
Nice.
How did Rogers?
You didn't respond.
So when you go towards the left, you're reducing whatever is in solution. And so that means like you're adding electrons back to it. And then when you oxidize it is when it removes the electrons. I still do not know what it actually tells you, like what information you can get from that.
Let's start from here. Suppose we are just conscienceless robots who just follow their prescriptions and just get measurements.
Okay.
What? Yeah.
Hey, boo.
What is the difference? Like if you take different samples, do you see peaks like this? And what happens to these peaks? Do they become taller, wider, shift to the left, shift to the right?
Oh, yes, they can become shifted. Why do they become shifted? I also don't. I really don't know that much about it.
Just tell your observations, but you are the biggest expert in this group.
But yeah, like if you have too much of your sample in a solution, you can get like really big peaks and really weird peaks because it just doesn't carry a charge very well. But
if you take different sample, like your samples are likely conjugated polymers. And they of certain lengths in solution, and they have like this connected together donor and acceptor groups, and you synthetically modify them. But if you have polymers that is more donoring or more acceptor, probably you guys name them accordingly. How the peaks are changing?
Increase or decrease, grow or shrink.
Yes. So reduction is at the top or at the bottom? What is the reduction? What is oxidation?
I'm assuming reduction is going to be your bottom because electrons are negative and reduction is the gain of electrons. While on top you have a positive potential. And so that's going to be your oxidation because it is the loss of an electron, so it is more positive.
Okay. Do you bubble argon? Why? What happens if you don't?
oh, you get some wonky data because you have like dissolved oxygen and sometimes water that's in there. And that will show up as really big peaks.
Or to the top or to the bottom, to the left?
On the top, on your oxidation side.
Okay, oxidation at the top, confirmed by.
Yes, confirmed.
Okay,
Confirmed.
okay, good.
Yeah. And so I've actually just been doing data with ferrocene because I've been doing like ratios with acetonitrile and DCM. And so I haven't been doing a lot of stuff with
Not yet.
complicated
Okay.
polymers, not yet anyway. Hopefully I will once we figure out why the hell our
Stuff doesn't work.
yeah, we keep getting crossing. And I don't know why.
I walked into group meeting today and Zach and Olivia were there. I'm like, Zach. You're here.
Why is that shocking?
I wasn't expecting Zach to be there.
Yeah, Brett, is he graduated like not that long ago? like
He graduated like right before I came.
Oh, okay, yeah.
Okay, so,
Yeah, like, Zach
the-
Jones.
what are common and LUMO orbitals? Did you hear about them?
Highest occupied molecular orbital,
Oh, yeah, and
lowest
lowest.
unoccupied molecular orbital.
I'm impressed. I'm in presence of highly educated people. Thank you. So. What are the, yeah, I shouldn't focus on myself. I should focus more on you guys. So, what about the, which orbital is higher? Homo or LUMO?
Homo, highest occupied, LUMO.
No, LUMO, because it's lowest unoccupied.
Ah, okay,
Ah,
okay. So LUMO is higher, Homo is lower. Because I don't
Oh, I
know,
see, yeah, you're right.
bow exclusion of bow fields at the bottom, okay. No.
I don't know, but why is there a scarecrow?
Oxidizers. What does it mean, oxidation?
You're losing an electron, the species that you're looking at. It's a metal typically,
But it is one losing, another is gaining.
yes.
So oxidizer is gaining,
No, oxidation.
oxidizer is,
The oxidizer,
is gaining, and the substance that is being oxidized is losing.
yes,
Yeah.
you're reducing.
Mhm.
Oxidation is lost, so if your oxidizer is gonna be the thing that is. Reduced, because it's
That
going,
gains an electron.
Yes.
Just reduce.
and your reducing agent is oxidized because it's losing a reagent, an electron.
Correct.
So oxygen attracts pulls electrons from others
Not necessarily,
sometimes,
yes.
because its orbitals are lower and they just, it serves as sink to pull electrons.
That makes so much sense on why oxidation is the way it is. Oh my god.
So
So what he just said was. The oxidizing agent, whatever gains an electron,
Yes.
is oxidized because its LUMO is lower than the HOMO of your
Oh.
reducing agent.
Okay,
And
yeah.
that's why oxidation reduction works the way it is. In a simplified term.
I wouldn't sign under each single word, but generally it is,
That was like a fairly good summarization of like what happened.
we can look the recording and just edit maybe a couple of words later.
Just
and then
put
we'll-
your voice in when Sam says it.
No, put Sam's voice when I'm speaking. It would be better. See, I have no accent.
Oh.
Okay, so occupied related with pulling electrons are homos.
Yeah.
And donating electron unoccupied lumos. So if this deals with oxygen, this will be homos occupied, this will be unoccupied. And they have different energies. So different species, you have different energies of homos and lumos, right?
Yeah.
And by practicing the cyclophotometry, one can literally measure energies of homos and lumos. So it is a chemical way to measure energies of orbitals. In connection to our class, that right now we are still with particle in the box, but we have orbitals. We didn't occupy them literally with electrons, right? But there are energies of orbitals, and at one point, experimentally one can measure them instead of computing. Okay, so here is one connection. Another connection is Nobel Prize in Physics 1986. So the name of the technique is scanning tunneling spectroscopy, scanning tunneling microscopy. So there is a substrate, and one places a molecule on a substrate, which is like conducting substrate and then molecule. And then one has a golden tip of sharpened to atomic level, like single atom on the edge of the tip. And one finds the molecule, pulls tip directly to it, and then scanning voltage in the same way as you do in cyclic voltammetry, right? And then depending on the voltage and energy levels of the we will get to it very soon.
Building up.
Together.
I'm just preparing. Depending on the resonance of HOMOS and LUMOS at the molecule and its resonance to the voltage, current does or doesn't go. So basically, scanning tunneling spectroscopy is a physics analogy of cyclic voltammetry. Okay, so it's a tool to measure should raise this one. It's yes. So here are energy levels like occupied, unoccupied, and then by changing the voltage, one makes offset between these orbitals and current. It is a way to measure the energies of orbitals. And when there are too many orbitals, they are not standalone individual peaks, but they are continuous distribution. And continuous distribution of a lot of orbitals, and sometimes instead of orbitals, people those states. When they are dense, it is density of states. So it will be main subject of today's meeting. Okay. So what do you see on the screen?
Sail.
Okay. And what's sail? What is the shape of the sail?
Triangle.
A right angle triangle.
Okay.
Approximately.
I think you're doing great. So here are the main characters of our today's meeting.
Scarecrow.
So Roman and the how do you call this ship you
Sailboat? A yacht?
A yacht?
Yacht. You should
Yachts
know.
don't have sails.
No, I know, but I don't know what he's looking for.
Thank you for teaching me. I never knew how to pronounce it in English. So you
Yacht?
yes, I would say yacht.
Yacht, yes.
Fair.
The CH is silent.
Why is
Really
silent?
YH.
I don't know.
Yeah, so it's
I
yacht.
don't know why.
So I go on the yacht to catch a salmon.
Yes.
Yeah.
I step out from castle into the yacht. What a wonderful language.
English is just three languages
I have no
stacked
explanation
on top
for
of
that.
each other with a trench coat. Makes no
So
sense.
this is a sailboat.
And
Pirate boat.
like 200 years ago, there were like 20 types of the sailboats. And depending on the shape of the sails, they have very lots of names.
Oh.
And I wonder, do you have any specific name for those that have the triangle sails?
No, most of them have like,
Yeah.
I know pirate
you would
boats
know
have
the
kind of
answer.
rectangular sails.
Right, so it's not a pirate.
Yeah.
no, I mean, like sailboats have the triangular sails. There haven't been like the rectangular ones since probably the 1850s.
Okay.
Why?
Oh.
Because that's when like
Stored in your information.
steam engines became a big thing.
Like
And
what?
then
Oh,
steam
steam
engine-
engine.
So then.
Wow,
there was
that
no-
does, that information
So
does not
then,
exist in my
therefore,
brain.
they change.
No, like.
Sorry that I know the history of machinery due to public education. I was mildly better than probably what you got because
Hey, how do you know your public education was?
you're in the middle of Bumfuck, North Dakota. I'm in the cities.
We
That's
the same
education was better than
I
mine.
know that.
What to eat?
All right, let's get back on track
Yeah.
here.
Oh, I have a second, now I have two supporters.
It's too political for me. You can argue about anything else.
So what's, here is, the main figure that we need to get by the,
Oh.
within the next half an hour. So, the reason to bring up this sailboat is to see that, the triangle shape and this like declining, decaying semi-triangle, it's like little curly shapes are density of states for one-dimensional particle in the box. So we need to derive this shape. And with this sail image, you later can teach quantum theory to at the kindergarten level on one hand, and on another, it will stick to our memory for sure. Why do we have this astronomy?
I love it.
What's the connection to physical chemistry and quantum theory?
Honestly, that one,
Huh?
Zach.
I'm not so.
Jack from Titanic.
Wind,
What?
it blows in the wind.
It scares crows away.
Yeah, but what about the little guy?
I was just in doubt which one is more representative.
Okay.
I can decide between these two nice characters.
I'm gonna be honest, I'm with Elsa on this one though. I don't entirely know because
Yeah, I can't, I
Feels
don't
like-
have an answer for you.
only like I don't know what connection could be made with like
The shape.
straw man. I mean, like it's a person. The shape is like
Not to make you draw that argument.
Yeah, let's hear it.
They're both made out of straw.
Yeah.
The only thing I can think of is that they're both made out of like a million different little tiny things that, you know, come together to make a shape. So I think that like.
and that's like a representation of your like data.
Yeah.
Okay, well, I like your idea much better than mine original idea. I wasn't putting straight logic. The thing that, it's only visualization too, but this scarecrow stromel will be used to imagine that we need to scan the energies, and like scanning of the energies, if you present it to the kindergarten, will be like someone is walking and looking, and not to offend any living persons, it will be a straw man walking along the line.
Hey, with the vase.
What was, the king, what was with the king?
Huh?
The king.
King?
Holding, yes, it was not trying to scan it, but.
I do not have philosophical background for the cane, but you can design one.
That's both exams.
Yeah, bro, I'm not even.
Okay, Elsa or Eva, who requested me to type?
I did,
Um,
thank you.
my pleasure. I didn't type it, well, I can pretend that, oh yeah, for your birthday, but it was different story. I was showing homework again and again, and from year to year, and just looking at it, I just decided to type, and then I forgot that it's already typed. But this is a code you will practice on Wednesday, and you run it in different circumstances, and then it will be your homework due on Friday. And this will be due in about 9 days on Wednesday next week. This one is not MATLAB, a little bit more challenging, so try to plan your weekend or time to invest a couple of hours. Okay, so here is where we are. We have an axis for different theories, an axis for different objects, and later on we will use the third axis for perturbation. So you can, with your closed eyes, you can reproduce equations for evolution operator, for Schrödinger equation, for Heisenberg equation, and maybe for density metrics. Today we will get the density of state. And yeah, we will write into this shape, which looks like sailboat. Okay. Now, two.
Excuse
Let's see. I hope you can.
Xavier's not here to take the other, this part.
So let's,
Yeah, right.
the goal is not to like torture anyone or put under question your knowledge. We just need to refresh a little bit of our background information to feel a little bit more comfortable. I know it sounds a little surprising, to feel a little more comfortable with class material. So,
Question,
yes,
the very last thing, it says, oh, dependence on blanks constant, never mind.
so you just need
What are you
to
doing?
put something into the,
There's a gap.
Yeah, because I accidentally pulled the table towards me. You have an entire table to yourself.
say, I model the shape of sail in a planner. So let's try to fill the boxes, and there are hints by text. So
Is this? Is it this?
I don't know what you're talking about.
Oh, that
But go ahead and fill.
does the same.
I see enthusiasm. So the energy of one-dimensional particle in the box has several factors that differ by their meaning. And let's try to memorize them, because our derivation that we are going to go over will depend on this thing. Basically, we are going to convert set of energies for particle in the box into the density of states. And to say B, we need to say A, right? So if you know the whole equation, just write it in an empty area. If you don't, try to refresh your memories by looking at what they mean. So let me bring a hint that may make you happy. So I will mute yourself. I will just mumble something that may assist if you have completely no idea. But I'm sure you can be developing. So classical kinetic energy is p squared over 2m. If we do it kinetic energy as quantum operator, we will get bar squared to masses in the denominator minus then gradient, the derivative of gradient. Or if you know the value of the number, if you like the value of the wave factor. What is this A? So I'm just pretending that I don't know the answer and trying to develop it. So if our wave function is by m over L times x. And everything in this area can be treated as K. And I may try to use this K, plug it in and see what happens. So kinetic energy, H bar squared, pi squared, M squared, L squared.
No,
It's on the floor, it's mine now.
no, the fuck it's not.
We are recording dramatic.
Yeah, we are on recording.
So it is my attempt. Your attempt can be much better because your memory are sharper.
I don't know about that one.
Really round. My move is really round.
Mine has smooth edges.
So then let's analyze. So Planck constant is here. Right? There's the mass of an electron. So Planck constant is in a second power, and it is in denominator. Mass is in the denominator. So the bigger the mass, this more energy. Now, dependence on the index of orbital. So index of orbital is this n that comes into particular in the box. And it is important that it is in second power. Second power comes from the fact that for the part G or for classical kinetic energy, it is like momentum squared. G over n squared. And then this L comes from an attempt to pick this harmonics, and they should be dimensionless. So we have here x and here lengths, and this length comes into denominator into the second power. So try to fill the boxes. It's better to write a little bit wrong than not write at all.
Are you gonna watch me, right?
Yes.
Okay.
I have a great pedagogical idea.
Oh, no.
Yes.
No.
Dimitri,
This is your punishment.
No, it's your reward. So just try to feel whatever you feel comfortable with this. Just try to use in the box.
You just.
Right.
So the first one, yeah.
Okay, so this one depends on the size. So that should be,
And actually, this is all wrong.
it should have bits
Yeah.
of length, so it should be L in this box
Huh?
of some kind.
Just wrong.
Good job.
How do you know what it is? It's just L?
Is it L?
No.
What is it?
I'm not saying you're wrong, I don't know.
Something, like,
Okay, Mel,
would it be
Like-
1 over L?
if the dependence on size, the smaller the box, the larger the energies is, where do you think the L is?
On the
Nominator.
bottom.
Okay.
Overall?
Keep it L in each
Square.
power. Okay, yes, thank Melody. Thank you. So Sam, you already showed me, so it will be boring for me to watch your progress.
His progress or his. Looking at the slides.
Ava, your turn.
I could have,
Dependence on index of.
Dimitri, I don't know at all.
Me too, me too.
What, okay, what
You
variable
always
is,
know the
what
answer.
variable is associated with the index of the orbital?
what?
And is,
Think back to Roger's
and is
class.
non-linear.
Melody, think back to Roger's class.
I'm just thinking out
I
loud
would say
here.
orbits. What
N,
variable?
it has to do with variable.
So
N.
you can fill any box which you feel better. And I do not guarantee that my answer is absolutely correct, but you can like navigate and make connections. So maybe left box, one constant,
Non-linear.
is it a numerator or denominator?
It increases with this.
Yeah.
index.
On the top, nominator.
Okay, so left box, I would.
What? H squared or G?
Oh, wait, N.
I would write an H square in the left box, like.
Oh, we're bringing black box.
Oh, man.
Okay, let's find it.
Such a friend, Frederick.
And do a roll. Elsa, you're up.
Elsa, we need to do a box.
Elsa's up. I believe in you, Elsa.
I myself this time, actually.
And if your research is on conjugated oligomers.
Yeah,
It is
and
yours.
so if I get this wrong, Seth has to fire me.
Oh, yeah, the opening and
I
stuff.
saw stuff this morning.
I didn't say that, it's not on the record. You have to edit it out of there.
So
I'm not
either,
gonna watch this.
So for the third box, because the mass of the electron would can make it either smaller or larger, I feel like M would have to be on the bottom, correct?
Yeah.
So good.
I'm proud of you.
okay, like that, yeah, thank you. Thank you. Frederick, it's your
Frederick,
moment of glory. And Frederick has a privilege to fill the most important box.
Oh,
Let's
I have
go.
no idea.
Come on with your lucky yellow hat.
That is an ugly yellow.
Fred, of the
I
Frederick,
mean, I'm just looking at what we haven't put
Yeah.
on there yet.
correct. That are circled, what one's not on there yet?
I squared.
Mhm.
And
That's not a, that's not a
What's
pie,
yours?
bestie.
And what else? I squared, sure.
What else is that?
Oh, what else is there?
What
What
is
letter is
here?
that
What
that's
is
Next to it.
What is,
Oh,
what is here?
oh, we have two H's, right? Yeah.
It's not
Where?
H, and number of.
It's not an
indexes.
H, it's an N.
Big chief.
Oh, I see, I see.
Oh,
Perfect, that's perfect.
Yeah. Good job, Fred.
Right.
Okay.
wasn't as scary as
Now I
thought.
can,
Pass.
Oh, I need to add my pie square. Oh, you can use mine now.
so now you are certified experts in energy of particle in the box. right?
Fine experts.
I need to issue certificates, and you put it in a frame.
Yes. I'll magnet it to my fridge.
Okay. So density of states, there are some boring words, you'll read them.
Because we're learning them from you.
You have to kind of do. The idea is that if the number of levels is like in your quiz, you did have mass in the denominator. If the mass is big, then the levels will be dense.
Yeah.
And there will be too many of them to look at them simultaneously. So and if you want to compare models, systems of different nature, they may have sparser or denser states, and more than 1,000, more than 100. Looking on individual orbitals is not practical. So we need to do something with this. Now, I will block the video, draw something, and then return back. So that's because it will be, otherwise you will be bored and sleepy. I will.
Okay.
So we do have access of indices of quantum states. So we have That's better, let's do it differently. Let's put here, we put number of quantum states, and here is energy of quantum state, number m, divided by energy of quantum state number 1. Why do we do this trick?
Ratios it out.
Ratios is dimensionless. So what is the answer here? E sub n divided by E1.
But E1 is where n equals 1.
Minus E sub n
Not
minus.
subtract, divide. So in the numerator, you have n squared. In the denominator, you have 1, and everything else is the same and can be cancelled. What is it, Kutu?
It's just e to the n.
E to the n.
Which is n squared.
N to the power.
Of 2.
Yes. Okay.
Plus 1.
So state number 1, state number 2, state number 3, maybe number 4. So the energy of state number 1 is 1 in this dimensionless, right? The energy of state number 2 is 3, 4. 2 squared is 4. The for state number 3, 2, 5, 6, 7, 8, 9. 9. For 4, 10, 11, 12, 13, 14, 15, 16. 16. Now let's bring up this
Oh, running.
straw man.
Yeah.
Love the base.
Looking at. This feels like a sound. I know.
And, let's this straw man to walk along x-axis. And let me turn his head. You go forward and look back.
Yeah,
Okay?
yeah.
So, and his task will be to tell how many quantum states he found behind. Like, he walks along energy and he tells number of states behind him.
Oh, yeah.
So if you're at number
Like,
one,
choose
it would be zero?
Zero. Then after he passes this point, he looks behind and he finds one. After he comes here, he looks behind and finds
Two,
Two, okay, so it's a stepwise function.
three,
okay,
and
three,
then four.
and then four. So
Because yeah, H can't be anything less than a whole number.
we can call it N of E. So, and the observations of this straw man can be called number of states.
Because yeah, states can only be whole numbers, right?
Okay. Now, let's bring up a derivative. If the straw man is our loyal servant, a robot, and he has a wire connecting from his head to our computer, and we do continuous measurement of this value, right? And now we are smart scientists who have all tools in front of us, and we want to take derivative of this function. We can do it, right?
Derivative in terms of,
Derivative, let's put it. This one is E n of E, and we will do D n d E.
okay,
Use the same E sub n divided by E1. So when the function is flat, what the derivative is
zero.
0. When the function experiences steps, the derivative is
1,
Undefined.
undivided.
Yeah,
But when that's.
I mean, that just means it's undefined, because it just
infinite. Then
instantaneous.
infinite. Infinite. Infinite, right? So it looks like a spectrum.
Yeah.
Right? And it is interesting that these peaks appear at the energies which are exactly equal to the eigenstates. Yes.
Okay, so this might be a weird question, but so this graph that you just drew kind of looks like the graphs we were looking at for Fourier transforms. So is that something you can do with this?
Yes, it is very possible. We are not going to do it now, but it is a legitimate connection. Yeah, thank you. I will draw on the board until as long as I can, and then I will squeeze the rest in like 2 minutes. So it is a definition. The dn over de is referred is as density of state.
Okay.
If they are sparse, it is just a peak. But if there are many states, if the little m is not little, they are dense, and then one needs to go to continuous minimum. So the infinite function is indefinite, and it is not comfortable to work with. But we have a freedom of science. We can do any cheesy approximations. And we can replace the peak with a Gaussian function. Each peak is a Gaussian function. Then, and it is defined everywhere. Then we will say that density of states by alternative definition is summation over quantum states e to the power, here is a normalization, square root of whatever it needs to be, minus energy of quantum state squared, and here we have a width parameter. And when we bring them all together, it will be a continuous function. In the area where this Gaussian peaks overlap, it will be bigger. They will be unresolved. Okay, makes sense? So I am going to erase it and do, yes,
One over the square root of what?
just repeat.
It says just one over the square root.
That's the normalization.
Normalization, like 2 by this width parameter. We can look on German money and as a cheat sheet for exact shape of the normal distribution. Okay, I'm going to erase it and do one more step, and then it will be time to rush and show slides again.
So,
Rush what?
no Russian, I don't think.
Can you read the bottom
Rush
part?
right now, right now.
The bottom part.
Let's say, I think Fred got.
Yeah, not a.
The physics
Not cheery
behind
reference.
Yeah, thank you for friendly, interesting and pleasant note on the board each morning. I enjoy reading them.
Thank you.
So,
This is not Chem 101.
I said the physics behind chemistry 101.
We didn't even take Chem 1.
There is no 101 chem.
What's the lowest? 121?
117.
Oh.
Yeah.
No,
Okay,
Oh, that makes sense.
I have the credit for that.
energy of N
Oh.
is square, right? And now we need N as function of energy. How do we get, if the states are very dense, so that the points are like dense and dense and dense and dense. And we need to look for index of state as function of energy. If this one E n divided by E1 is n squared, what is n of let's say number of energy? How do we do that? So we do mirror image of a function in respect to the line x equals to y, right? So it will be this function.
So it's gonna be
It's a square root
Yes.
function.
Square root of what?
square root of the entire. E
Of
of N.
energy. Okay. Now, you have another class. It will be much easier to do this bit of derivation on the board, but I'll better rush and show on the screen because we need to be in time. So focused. Start, go. So Stroman that we already covered. Here overlap, definition of density of states, delta function is just this thing. So two alternative definitions. Properties of derivative of step function is delta, integral of delta is step function, two definitions. And here is what we need to get. If the states become sparser and sparser, the density of states will be lower and lower, and we will get the shape of the sea. So here is what we have. If inverse to square is square root, and now we do have the number of states behind the Stroman is the energy, dimensionless energy into the power of 1/2 square root. Agree? Now we plug in this number of states into definition of density of state. We just take a derivative of a square root. What is a derivative of square root? How do we do derivative?
1/2.
Yes, the power minus 1. So it will become negative 1/2. So the power negative 1/2, how do we draw it? So
It's 1/.
1/x declines, and 1/square root of x declines, but not as quick.
Low.
Low, exactly. And basically, this is the answer. We do have density of states for the particle in the box as factors times 1/square root of energy. This gives us only one shape, one line. But if we do have several bands, if you have other quantum numbers or other dimensions, they will create replicas of this thing that will have higher energy for electrons and flipped backwards lower energy for holes or for like occupied orbitals. This observation can be seen in conjugated polymers, and they are very well seen in carbon nanotubes. Okay, the name for this seal shapes are Van Hoff singularities because it is a scientist who discovered them. And yeah, we know the game that they can be measured, and this is end of the meeting.
And then, okay.
Yeah, thank you much for your interest, dedication, and questions. Looking forward to seeing you on Wednesday.